Okay. How's everyone doing? Are we all doing good?
Yeah.
Wonderful. All right. Okay. So today we're going to be talking about continuity and one-sided limits, though we've kind of already talked about one-sided limits before. So part of this should seem familiar. Okay, so you got homework due Monday. It looks like everybody turned in the homework due last Monday or this Monday this week, and I'm gonna get all that graded over the weekend. Get you some feedback. Okay. Discussion post this week is for participation points. I've been seeing a lot of people posting, and you don't have to have anything super deep for that discussion post. You just want any old idea of a limit, okay? In real life. And then next week, Thursday and Friday, everybody will be online. I'm gonna be out of town. My sister-in-law is getting married. My wife's younger sister is getting married, and so I will be out of town. But we will have class online. Okay. So make a note of that. Fully online next Thursday and Friday, September 10th and 11th. Do you have your green pass? I guess I believe you. But if you show it to me, that'd also be good. All right, any questions on perfect. Any questions on announcements? Okay. So last time we talked about several different methods for finding limits analytically or algebraically, however you want to describe it. There was one example that I didn't quite get to, and that was the limit as x approaches 0 of sine of 3x over x. And if you ever see this type of limit, the idea is to use, I showed that the limit as x approaches 0 of just sine of x over x, I showed that this was equal to 1. So to show that the limit as x approaches 0 of sine of 3x over x approaches something that you need to find, the idea is to use this and bootstrap your way up to this answer. So the limit as x approaches 0 of sine of 3x over x almost looks like that limit I have written there. But in the first limit I wrote down, the stuff inside of the sine has to match the stuff in the denominator, right? And I've got sine of x over an x. Here I've got sine of 3x over an x. So the idea is if I multiply top and bottom by 3, so I'll do like that. I multiplied top and bottom by 3, so I haven't changed anything. But now the inside matches the bottom, right? So, and then this 3, this is just a constant, and so I can bring that outside of the limit. So this is equal to 3 times the limit as x approaches 0 of sine of 3x over 3x. And then now I can just rename 3x theta if I wanted to. And then as x goes to 0, 3x still goes to 0. So this limit, sine of 3x over 3x as x goes to 0, is still just 1. Does that make sense to everybody? Because we can pretend that, again, 3x, we can call that theta. And then as x goes to theta, or x goes to 0, theta goes to 0. And so this limit is just 1 on the inside here. And so I'll just be left with 3 times 1, which is 3. Okay. Are there any Oh, can you guys not see the notes online? Oh, everybody can see them? Okay. If you can't see the notes online, then it's something on your end, just so you know. So, but these will be uploaded in case anybody can't see them online. All right, so do I have any questions about this limit though? This is the key step, recognizing that the limit as x goes to 0 of sine of 3x over 3x, that's just the same thing as the limit as theta goes to 0 of sine of theta over theta. As long as you have the stuff on the inside of the sign matching the stuff in the denominator, you can apply this limit, that limit right there. Okay.
Professor Matheson,
Yeah.
just to clarify, since the stuff in the square that you boxed in, that became 1,
Yeah.
we took the 3 outside and multiplied it by the 1. That's where the 3 came from at the end.
Exactly. Yeah, exactly. So to be perfectly clear, this limit that I have written down that we wanted to find, this limit is 3. So your final answer, if you have something, if I ask you a question like this, your final answer is going to be 3. Okay. So that's how we tackle a problem that looks like that. 3. All right, so today we're going to be talking about continuity. And so our favorite functions for when we evaluate limits, our favorite limits to evaluate are when we can just plug in the number that we're looking at, right? I hate having to draw the graph and then cover up what's happening because it could be weird. I love it when I can just plug in x equals a when I'm looking at the limit as x approaches a of f of x, right? So there's a special name for functions like that, where you can just plug in the number that you're looking at. And those functions are called continuous functions. And continuous functions are defined by this equality here. So a function is said to be continuous at a if the limit as x approaches a of f of x is f of a. Any questions on this? This is just the definition. We were using this a lot the other day for functions that actually I didn't tell you, but functions that were continuous. And so we were using this a lot. Today I'm just defining what it means to be able to plug in a value. That means that that function is continuous at that point. Okay. So if a function is continuous at every point in an open interval, C to the D, does everybody know what this notation means here? When I'm talking about an open interval, C to D. In case anybody doesn't know, this is just the set of all x, or all the x's between and not including C and D. So this is x greater than C and x less than D. Okay? That's what that open interval means. So if a function is continuous at every point in an open interval, then we just say f is continuous on that open interval. Okay? And lastly, if f is continuous at every point for every number, then we just, most of the time I'll just say f is continuous. If I don't say continuous at a point or continuous on an interval, I just mean f is continuous at every point that you could possibly think of. Okay? Sometimes I'll say it's continuous everywhere. Most of the time, I will just say the word continuous in this situation. So, some things to note. Another way you might want to think of a continuous function is as a function whose graph you can draw without lifting your pencil or your high-tech Apple pencil. Is it pencil? Apple pencil, right? Yeah. Without lifting up your pencil when you're drawing the graph, if you can do that, then that function's continuous. If you have to pick up your pen at any point, so for instance, if I'm drawing, if this graph is continuous, because I never had to pick up my pencil, but this graph, I have to pick up my pencil to jump up here. That graph is discontinuous, the graph in the red, okay? And by discontinuous, that just means not continuous at that point. All right, so the definition of continuity implies that f of a exists, which we hadn't assumed before. Before, we didn't care if f of a existed or not, because I just told you draw a line over x equals a, and then don't worry about what actually happens at a. Now, for continuous functions, we have that f of a exists and it equals that limit. So continuous functions aren't trying to trick you when you're looking at a limit. Okay. So if the limit as x approaches a of f of x is not equal to f of a for some point a, we call a discontinuity of f. If I ever accidentally say singularity, I mean discontinuity. I've been saying singularity for years with my research. And so, and so if it slips out, I'm sorry, I mean discontinuity, okay? Discontinuity. Yes. And then, so there's gonna be 4 types of discontinuities that I want you to be able to recognize. Okay? Let me, I think I had there was a question in the chat. Chat. Oh, yes, thank you. Yeah, in my notes, I accidentally wrote with. You can draw, if you can draw without having to lift. It should be without. Without there. Thank you. Okay, so there are 4 types of discontinuities that I want you to be able to recognize. First, what's known as a removable discontinuity. And a removable discontinuity is the only type of discontinuity where the limit as x approaches a of f of x exists, but is not equal to f of a. Okay? The reason we call this a removable discontinuity is that I can literally remove the discontinuity by just redefining f at a. So here, as you can see with this function f of 0 is equal to 2, but the limit as x approaches 0 is -2, right? Does everybody see why the limit as x approaches 2, or why x approaches 0 is -2 here? Because if you just cover up x equals 0, let me do it. If you just cover up x equals 0, then it looks very much like the function is approaching -2 and not +2. Okay. So I could remove the discontinuity simply by saying, well, instead of f of 0 being 2, like we have defined here, like clearly this is just designed to trick you. Instead of defining f of 0 to be 2, I will redefine it to be f of 0 equals -2, and that removes the discontinuity. When you do that, all of a sudden this function becomes continuous. Okay, so that's removable discontinuities. And then there's 3 types of non-removable discontinuities that I want you to be able to recognize. So the first type of non-removable discontinuity is a jump discontinuity, okay? And a jump discontinuity looks just like this. It jumps, the function jumps from one value to another, or the limit rather jumps from one value to another. So with a jump discontinuity, we have, if I cover up this line here, if I only look at, say, what's happening as we approach 0.25 from the left, well, it looks like we're approaching -1, right? So it looks like the limit should be, if I'm looking at it from the left, it looks like the limit should be -1. And then if I zoom out and then zoom back in, and now only consider what's happening to the right of 0.25, well, now it looks like the limit's approaching whatever that is. That happens to be 1. So if I look at what's happening from the right, the limit looks like it should be +1. This is an example of a jump discontinuity. And in this example, the limit doesn't exist, right? The limit as x approaches 0.25 of f of x fails to exist because it's approaching two different things from the left and from the right. And we're going to see in a minute that the way we write that is that the limit as x approaches 0.25 from the left of f of x is not equal to the limit as x approaches 0.25 from the right of f of x. That's how we write that. Okay. So that's a jump discontinuity. The left and right hand limits don't agree. The definition of a jump discontinuity, and we can't, it's non-removable because there's no way to redefine f at that point that we're approaching to make this continuous. Okay. Are there any questions about jump discontinuities? These are, when you're looking at a graph, these are usually the easiest to point out and say, oh yeah, that's clearly, I have to pick up my pencil there to jump from going from here, you know, coming from here to up here. Okay. All right, so that's jump discontinuities. Another type of discontinuity I want you to see, and we've seen this before, is I call it a sine of 1 over x discontinuity. This is a removable or non-removable discontinuity because, again, this time the limit just fails to exist. Oops. And if I cover up, if we look at the limit as x approaches 0 of f of x, it doesn't seem like it's approaching any one value, right? That limit, this function's bouncing back and forth between plus and -1. There's no one value that this function is approaching. And so this one, the limit fails to exist. Limit as x approaches 0 here of f of x, d and e, which stands for does not exist, right? Any questions on this type of discontinuity? Okay, this one, both the left and right hand limit also don't exist. In the previous one, the left and right hand limit existed, but weren't equal. Here, the left and right hand limit, those themselves also don't exist. So if at any point you have a limit not existing as you're approaching some point, that's a sign that the function has a discontinuity there, okay? All right, and then lastly, an asymptote type discontinuity. And an asymptote discontinuity is where a function is blowing up as you approach some value. Okay, so here we have the function as x approaches 0. I mean, I cover that up, but it doesn't really change anything. As x approaches 0, from the right-hand side, we're still blowing up to infinity, right? That doesn't, we're not approaching a single value, it's blowing up, and so I can't approach f of 0. F of 0 doesn't exist at all here. And similarly, from the left-hand side, we're going to negative infinity, right? So this type of continuity, or discontinuity rather, is defined by the limit, the limit as x, in this case, approaches 0, and we'll just look at, say, the right-hand limit of f of x equals, quote unquote, infinity, okay? Again, I put quotes around equals because infinity is not a number, and we're gonna actually tomorrow we're going to define precisely what this means. But for right now, it's enough to say, oh look, it blows up at 0 for this section on the homework. That's sufficient to describe an asymptote discontinuity. These types of discontinuities happen when you're dividing by 0 in a function. This function here is just 1 over x. I plotted the function 1 over x. Okay, and so you'll always get one of these when you have a function where you're dividing by 0 at a point with nothing in the numerator to sort of cancel out that division by 0. Okay, so let's look at a specific example of that. Where does the following function have an asymptote or asymptotes? You can have more than one asymptote. Okay, and these are specifically vertical asymptotes. Okay, so how would I find, there should be an x squared there. Sorry, guys. This should be x squared. There we go. So how would I find the asymptotes of this function, if any?
Do the ratio of x squared.
What do you mean by that? Oh, I think I know what you mean. I think you're jumping ahead, I think. You mean divide 1 by 1 there? That's for horizontal asymptotes, which is very good to know. But I want to know, what about the vertical asymptotes, which are defined by that limit as we approach a number blowing up? And I think someone actually answered in the chat factoring, and that's exactly right. We're going to factor the top and bottom, and then see where, if I have any cancellation, I'm not going to get an asymptote where things cancel out. But if I have something in the bottom that's not getting canceled out and is 0 somewhere, then I'm going to get an asymptote from that, a vertical asymptote. Okay, so the top factors as what? We have x squared plus 2x minus 3. So what is the top factor as? It's going to be something like, gotta be x and x there. I need two numbers that multiply to get -3 and add to get +2.
X plus 3x minus 1.
Perfect. Everybody knows it. +3 minus 1. Okay, and then the bottom, I have x squared plus 4x plus 3. So I have x and x. I need two numbers that multiply to get 3 and now add to get 4.
X plus 3, x plus 1.
Perfect. X plus 3, x plus 1. All right, so the x plus 3 cancels, right? As long as x isn't equal to -3. But if x equals we can't ever have x equal to -3, but this cancellation indicates that there's a removable discontinuity there, okay? So we're left with f of x equals, this is for x not equal to 3, or -3 rather, but that doesn't even really matter. F of x equals x minus 1 over x plus 1. So who can tell me where is there going to be a vertical asymptote for this function?
-1.
X equals -1, perfect. because we just take the denominator. There's nothing left to cancel it out in the numerator. We take the denominator and set it equal to 0. And that tells me that this equals 0. And that tells me that x is equal to -1. Okay. Any questions on that? Cool. Yeah, finding vertical asymptotes with rational functions will always boil down to this. Back to the top, back to the bottom, see what cancels, and what you're left with in the bottom, as long as it equals 0 at some point, that's your asymptote, your vertical asymptote, okay? All right, we're blazing. Okay, so most of the functions that you guys know are continuous everywhere they are defined, okay? And so we're going to use that fact very freely when we're evaluating limits. So examples of continuous functions that you know, all polynomials are continuous everywhere. Every polynomial, I mean, if you just think about how you graph polynomials, you never have to pick up your pencil, right? They're either roughly U-shaped or roughly like a cubic shape. I mean, with variations, but that's how they all look. You never have to pick up your pencil to graph that. Rational functions. These are continuous everywhere they are defined. And you might say, Chase, that last one you just said, it had an asymptote discontinuity at x equals -1. Yeah, but that function's not defined at x equals -1. When we were looking at this function here is not defined at -1 or x equals -3. And so it doesn't make sense to say the rational function is continuous there because it's not even defined there, okay? So this rational function, to be clear, is discontinuous at x equals -3 and at x equals -1. It has a removable discontinuity at x equals -3 and an asymptote at x equals -1. Okay. Similarly with these rational functions, these are continuous everywhere they are defined. And so that first one is continuous everywhere except for what value? X equals -1. Very good. Yeah, at x equals -1, this function's undefined. Does everybody see why? Because we're dividing by 0 if we plug in x equals -1. Okay. But that function, again, that's why it's undefined there. It has a removable discontinuity there. And if you want to see that for yourself, again, factor the top, and then a factor of x plus 1 will cancel. Okay. Where are these two functions discontinuous? Well, that's the same question as where are they undefined? So what numbers can't you plug into those? Yeah, 0. I can't plug in 0, right? So these functions are discontinuous at x equals 0. Discontinuities. This one is x equals -1. Discontinuities. Okay. And again, it's because those functions are undefined there. Everywhere else, they're continuous. Other functions that you know that are continuous, again, everywhere they are defined. Algebraic functions, which is like a square root of a polynomial, or really any root of anything, and a combination of powers of x. Algebraic functions are pretty general. So with this first function, it's not discontinuous anywhere. It's continuous everywhere. I can plug in every x. That function is defined everywhere. Oh, okay, that's fine. And then what about this function? Does that function fail to be continuous anywhere? What's the one thing that makes this weird? Or hard to work with, I guess.
There's a number outside of the square root.
Yeah, there's a number outside of the square root. And in general, the square root is making things a little wonky here, right? So the number outside the square root, I mean, constant functions are continuous. That was one of the first things I proved when we were talking about limits, right? So the only issue could come from the stuff under the square root. So where is a square root defined? What numbers are you allowed to plug into a square root?
Positive numbers.
Yes, you're allowed to plug in positive numbers and 0. You can plug in 0 into the square root, right? So that means this function is only defined for 1 minus x squared greater than or equal to 0. Does that make sense? In order to plug in an x, I have to make sure that 1 minus x squared is 0 or bigger. And then that tells me that well, I'll just add x squared to both sides. 1 is greater than or equal to x squared. And that means x has to be between -1 and 1, right? So that function that I have circled is only defined for x between plus and minus 1. It's continuous there. It's an algebraic function, so it's defined there, so it is continuous, but it is discontinuous everywhere else because it's not defined everywhere else. Okay, so finding those is going to be important to be able to do. Okay. And then lastly, trig functions are continuous. Again, everywhere they are defined. Sine and cosine are defined everywhere, so they're continuous everywhere. Tangent of x, well, that's sine of x over cosine of x. So tangent of x is not defined where cosine of x is equal to 0, right? And so if you want, you can look at a plot on Desmos, and I'll show you the discontinuities. I'll pull up a plot of that at the end of class so you can see the discontinuities of tangent of x. Okay, they're all asymptote discontinuities because, again, we're trying to divide by 0. And whenever you try to divide by 0, you're going to end up with an asymptote if there's nothing to cancel out the division by 0. Okay, so in addition to all these functions that you all know, they're all continuous. And if you take compositions of them, that's also continuous. So for instance, like if I take 1 plus x squared, and then I compose that with another polynomial, I cube that. That is a continuous function. Okay. And then, for instance, sine of cosine of x. That's continuous. So taking compositions preserves continuity. All right, so let's look at some properties of continuity and then use these in some examples. All these properties follow exactly from, if you remember that table that I showed you for calculating limits, this is just that table, but now where we had those L's and M's, now we can replace those with f of a and g of a, okay? So all of these are the same as that table, same as table, but we just have a little bit more information now about what the limits actually are when we're evaluating them. Okay. Are there any questions about any of these properties? Okay, let's use some of these to evaluate limits. All right, find the limit if it exists. So the limit as x approaches 3 of 2x squared minus 5x divided by x cubed minus 2x. Sorry, minus x squared. I'm tired. So how would we evaluate this limit? So the first question to ask is this limit, or is this function really, continuous at x equals 3? Because if it is, we can just plug in x equals 3. So this is a rational function, and that means it's continuous everywhere it's defined. Is it defined at x equals 3? Yeah. This is sort of a trick question, sort of not. It's a trick question in that you can just plug it in. I'm not trying to trick you into making you factor the top and bottom and cancel anything. No, if I plug in 3 into the bottom in particular, I'm not dividing by 0. This function's defined at 3, at x equals 3, and so we can just plug in x equals 3. Okay, and so by continuity, we have the limit as x approaches 3 of 2x squared minus 5x divided by x cubed minus x squared is equal to, well, I'm going to get, I just plug in 3. So 2 times 3 squared is 9 minus 5 times 3. And then I divide by 3 to the third, which is, I'll just write 20, that's 27, minus 9. Okay, and so some simplification. 18 minus 15 is 3. 27 minus 9 is, it was something. 18 maybe? Possibly. And then 3 over 18, if you want, you can reduce that to 1 over, what, 6? Okay. So, continuity, great. You can just plug things in. What we always want our limits to look like. Okay, are there any questions about this? So you might ask, wait, when will I know if something's continuous? Most of the time it's going to be when you have something, again, that you know, like polynomials, rational functions, trig functions, algebraic functions. Those are continuous everywhere they are defined. So if you have something that's not obviously trying to trick you, that's not like piecewise defined, then try plugging in the value first, and most of the time that'll get you where you need to go. Okay. I didn't even need that extra slide. All right, this one I will need the extra slide. What should C be below so that the function shown is continuous? So we've got f of x is 3x squared plus 2 for x less than or equal to 1. And then it's x cubed plus c times x. C is what we need to find for x greater than 1. So if we plot a graph of what's happening here, here's 1. So f of x is 3x squared plus 2 for x less than 1. So 1, 2, 3, 4, 5, less than or equal to 1. So this looks like what? It goes through, hold on, 0, 2, 1, 2, and then it goes up to 5 like that, and then it does that. So that's what this function looks like to the left of x equals 1. And to the right, well, I don't know what c is. So it's doing something funky, right? It's doing something like, I don't know, this, where I put this point depends on c, but it's doing something like this. So clearly, we need to find out c so that that point and that point line up, right? Does that make sense to everybody? Okay, so how would I find that C value then? Well, what is this point here? How would you find that? That's f of, well, the way I have it drawn, it's a little, it's not quite f of 1, right? But it is the limit as x approaches 1 from the right. Does everybody see that? That this dot that we want to find and move up to here, it should be the limit as x approaches 1 from the right. Okay, but what is the limit as x approaches 1 from the right? Well, as x approaches 1 from the right, we're only interested in that part of the function, right? That's the only part of this function that lies to the right of x equals 1. So then what is the limit? The limit as x approaches 1 from the right of, again, we only care about the x cubed plus cx right now. X cubed plus c times x. Well, I haven't mentioned this, but hopefully it's obvious that for continuous functions, the left and right hand limits, also you can just evaluate those by plugging in the number. So this is a polynomial. It's continuous everywhere. So what do I get when I plug in x equals 1? Well, my answer is just going to depend on c, right? I'm going to plug in x equals 1. So I'm going to get 1 cubed is 1 plus 1 times c. That's c. Okay. So coming back to my graph, this is at a height of 1 plus c, right? What is, let me draw it in red. What is this point? What's the height of this point here? How would you find that? That point is at a height of, well, what information haven't we really used yet?
Anything from the other function?
Yeah, exactly. I haven't used anything, any information about the function from the left, right? Well, this function is at a height of, really, technically, the limit as x approaches 1 now from the left. Does that make sense? So we want to compare the left-hand limit and the right-hand limit. Well, oops. The left-hand limit, that one, we only care about the top line here, right? 3x squared plus 2. 3x squared plus 2. But what is that limit? The limit as x approaches 1 from the left of 3x squared plus 2? Maybe someone in the chat. Yeah, exactly. It's 5. This is, again, 3x squared plus 2. I'm approaching 1 from the left. 3x squared plus 2 is just the polynomial. It's continuous everywhere, so I can just plug in 1. Because, again, the left and right-hand limits for continuous functions work the same way. You can just plug in the value. So I'm going to get 3 times 1 squared, so 3 plus 2, which is 5. So I want this to equal this. So what does C have to be? Yeah. Someone held up 4 fingers. I assume that means C is equal to 4. And so when you make that choice of C, then this graph turns into something that you can draw without lifting your pencil. It does something like that then. Okay. Are there any questions on this? Oh, it is 8:45. All right, so one-sided limits, thankfully, we've already talked a lot about one-sided limits. Those are limits that we consider only from either the left or from the right. The limit of f of x as x approaches a from the left is denoted by this, the limit as x approaches a to the little minus. So this is, that right there is how I indicate from the left, the limit as x approaches a from the left of f of x. Okay. And the limit of f of x as x approaches a from the right, well, now we use a little plus to indicate, this is happening from the right. I don't care what's happening to the left. I only care what's happening to the right of x equals a. Okay. So here's an example of a one-sided limit. What's the left-hand limit here as x approaches 0.25? Limit as this should be 0.25. The limit as x approaches 0.25 from the left of f of x is equal to, well, for that I only care about that, right? So that should be equal to what? -1. Very good. Very good. Does everybody see that? Does everybody see why? Because again, you might as well ignore the other half of the graph. When I do this, oh, it's obvious, right? Like clearly that's going to -1. What about from the right? Yeah, perfect. You guys don't have to raise your hands, by the way. Just shout at me. I'm shouting at you. You guys can shout at me. Yeah, exactly. It's +1. Because again, just zoom in, cut off everything that's happening to the left. Boom. Like clearly, it's got to be +1, right? So there we go. So something that we've used, a fact that we've used, and I've never formally said it, but when we're calculating these limits, the limit as x approaches a of f of x exists if and only if the left-hand limit as x approaches a of f of x is equal to the right-hand limit as x approaches a of f of x. And like I said, I've used this result implicitly when I've said, look, from the left it's approaching one thing, and from the right it's approaching another. The limit doesn't exist. Okay, that's exactly what this is saying. If the left and right hand limits don't equal each other, then the limit overall doesn't exist. If the limit does exist, then the left and right hand limits have to equal each other. That's all this is saying right here. Okay, are there any questions about this? I saw it. Yeah, I'll show you that in a minute. All right. So last, we're going to talk about continuity on a closed interval to finish things up. I only define, if you were paying close attention, I only define continuity on open intervals. So if you want to define continuity on a closed interval, you need to use these left and right hand limits. So we're going to say a function is continuous on a closed interval, a to b, and the closed interval now, that just means, so this just means a less than or equal to x less than or equal to b. Okay, we're gonna call f continuous on the closed interval if first f is continuous on the open interval a to b. So that's a strictly less than x, strictly less than b. And then the left-hand limit, or sorry, the right-hand limit as x approaches a, as x approaches the left endpoint, is equal to f of a, and the right-hand or sorry, the left-hand limit as x approaches the right endpoint is equal to f of b. Okay? So a quick example, this function here is continuous on the closed interval -1 to 1. Okay? Because it's looking at the graph, it's pretty clearly continuous at every point between -1 and 1, right? You don't have to pick up your pencil to draw this graph. That means it's continuous. So the only points that might seem like maybe they're causing some trouble are that point and that point. But by our definition, the limit as x approaches 1 from the left, so that's this guy, of f of x is just equal to 0 from the graph, right? But that's equal to f of 1. If I just plug in 1, I get the square root of 0, and the square root of 0 is just 1, or just, sorry, square root of 0 is just 0. So that is f of 1. And you get the same thing on the left-hand side. The limit as x approaches -1 from the right is 0, which is f of -1. We don't consider the left and right-hand limits outside of the interval because those don't exist, but it would be a little silly to say this isn't continuous on the closed interval, right? Because I don't have to pick up my pencil the whole time in drawing this, other than putting it down at the start and just picking it up at the end. So that's why we call this continuous on this closed interval, A to B. Are there any questions? Okay, if there's no questions, there's you probably noticed on the notes there's one more page. I will get to this at the start of class tomorrow, the intermediate value theorem. But I don't think I assigned any homework on it, so you don't really need it for homework, but it is an important theorem. So we're going to talk about that at the start of next class. Okay? Please wipe down your desks as you go, and feel free to head out.